when we have a hydrograph, we may be interested to know which part of it is contributed by quick response flow. Among the direct runoff and base flow, we usually consider the latter as slow response flow. This is because it takes a long time to reach the stream and contribute to the discharge. For this reason, if we want to know the shares of discharge produced by quick response flow, we will need to segregate the base flow from the hydrograph. This technique is known as base flow separation. Straight line method is the simplest method for base flow separation. First, we can determine time interval n in days using an empirical equation. The unit of A should be in kilometers square. Then, we should identify the peak and associated point of time. We are now safe to find point B on hydrograph, which should be occurring n days after the peak. By joining the point at the beginning of rainfall, A, and B with a straight line, we can achieve our goal. The second method may be used after we identify point B. Rather than joining point A and B with a straight line, we extend the curve before point A until it intersects the vertical line drawn at the peak. This forms an intersection point C. Then, we proceed by joining point B and C. Line AC and CB denotes the demarcation of base flow and direct runoff. After we successfully separate the base flow, we will obtain a direct runoff hydrograph. Once we obtain the said hydrograph, we may correlate it with the contributing rainfall. Such rainfall is called effective rainfall or excess rainfall. Effective rainfall is defined as rainfall that is being discharged out from catchment as direct runoff without being retained by any storage components or infiltrated into the ground. If a hydrograph is associated with a hyetograph, then a direct runoff hydrograph should be associated with an effective rainfall hyetograph. Similar to the hydrograph we developed through base flow separation, effective rainfall hyetograph can be produced by subtracting the losses from storm hyetograph. The losses are usually expressed as phi index. Note that by multiplying the area under effective rainfall hyetograph with catchment area, we obtain total direct runoff volume. This should be the same as the area under direct runoff hydrograph. Let's look into an example. After a storm producing 45 and 25 mm of rainfall depth for 2 consecutive 4-hour duration, we obtain the following hydrograph of flow at an outlet of a 35 km square catchment. Let's see how we can calculate the phi index in this case. First, we need to separate the base flow in the storm hydrograph. Given the catchment area of 35 km square, the value of n is 1.69 days, which is equivalent to 40.6 hours. The peak flow occurred at the 12-hour mark, which means our point B should be located at the 52nd hour mark. Discharge of 4 Qmax is associated with point B. By using straight line method, base flow with a constant value of 4 Qmax is obtained. We can now produce a direct runoff hydrograph that exists from the beginning of storm to the 48 hours. By using trapezoidal rule, we can estimate the total runoff volume. Note that we need to change the unit of time from hours to seconds. As a result, the runoff volume is found to be 1.534 million cubic meter. The rainfall depth equals the division of runoff volume with catchment area. In this case, it should be 43.8 mm. The total rainfall depth over the duration of 8 hours is 70 mm. 43.8 mm of the rainfall has been discharged as direct runoff. This means 26.2 mm of rainfall is gone due to losses. By distributing such losses over the period of 8 hours, we obtain a rate of 3.27 mm per hour. This is what we call a phi index. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.